this video is about how the Laplace transform can be used as a shifting transform. So we have reviewed up in the top right corner the Laplace transform of y prime is equal to s times the Laplace transform of y minus y of 0. And also that the Laplace transform of y double prime is equal to s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0. If you don't remember how to do that, or that seems completely foreign to you, watch the previous video. Link will be in the description. Let's take the Laplace transform of the fourth derivative of y, which you can denote as y with a 4 in parentheses, so it's not confused as a power. So, we can, using our pattern, we can say that this is s to the fourth, because you always have s to the power of the derivative that you're taking, the power of the degree of the derivative that you're taking. So we're taking the fourth derivative, so it would be an s to the fourth, times the Laplace transform of the original function y, minus s cubed y of 0, and now we're going to decrease the s exponent one more time and kind of take the derivative of y of 0, if you will, so we'll get s squared y prime of 0, decrease the s again, s, take the derivative of y again, y double prime of 0, minus y to the third derivative of y evaluated at 0. So it's like you're taking the derivative of the Laplace transform of y. I hope that makes some sense. It's kind of a difficult thing to wrap your head around. But so as you notice, each time the s exponent decreases, the derivative of y increases. I hope that makes sense. If it doesn't, I would recommend just kind of taking a minute and looking at this, maybe pause the video and just see if you can understand the pattern that's going on here. So now we're just going to go over a little bit of a notation thing because it will come up in the rest of our videos. So as you might remember from high school, the integral from 0 to x of some function f dx can be written as, that whole thing can be notated as capital F of x. And then, so similarly, we can write that a Laplace transform of a function is some capital letter of whatever that function is, in this case y, or f of x, of s. And having the s in parentheses is what differentiates it from being a Laplace transform. So therefore, just another notation just to get your head around it, the Laplace transform of f of t would be capital F of s. Just those are equivalent things. If you see a capital F of s, that you can assume, at least in these videos, that it is the Laplace transform of some function f of t. So now let's look at a different case. So we have the Laplace transform of e to the at times f of t. And this, if we plug it into our Laplace transform equation, is 0 to infinity, the integral thereof, of e to the negative st times e to the at times f of t dt. And you can combine the e terms by subtracting the a from the s, and this will leave it in the kind of e to the minus something t, which will be handy later. So you get e to the minus, and then in parentheses, s minus a t times f of t dt. So then what you might notice is the Laplace transform of f of t, which can be written as capital F of s, is the integral from 0 to infinity of e to the negative s of t times f of t dt. So what's the difference between what we just wrote and the line right above? Well, really the only difference is that whenever there's an s in the line above, or in this line, we have an s minus a in the line above. So that's kind of the only difference we have. So we could say that capital F of S minus A is equivalent to the Laplace transform of e to the AT times f of t. Now let's do an example to try to demonstrate this. So if we take the Laplace transform of cosine 2t, we know that, let's denote that as f of s equals s over s squared plus 4. And we've done that in another video. The video will be linked in the description. Because the Laplace transform of cosine of AT is s over s squared plus a squared. So if a here is 2, then 2 squared is 4. So then what if we want to take the Laplace transform of e to the 3t cosine 2t? So here a is equal to 3 because that's the format we just found out above. So then we see that this is the same thing as before, but now it will be shifted. So it's f of s minus a, or in this case s minus 3, which is equal to, now just wherever there was an s before in the cosine of 2t function, we put an s minus 3. So it's equal to s minus 3 over the quantity s minus 3 squared plus 4. So all you're doing here with this shifting transform, which is e to some at, that is what shifts a function, is replacing whenever there's an s with s minus a. And that's pretty cool.